Hello everybody. So in this video we're going to completely characterize the so-called perfect fields. So we briefly recall the basic definitions. So a polynomial f with coefficients in some field k is going to be separable if it doesn't have any repeated roots living in some splitting field, of course. And by definition, the definition that I have for a perfect field is that every irreducible polynomial with coefficients in k is separable. Okay, so the main theorem says that if k is a field, then k is perfect if and only if its characteristic is 0 or it has positive characteristic and k to the p is equal to k, where by definition this is just all the p powers in k. Okay, so let's see how the proof goes. So first of all, we're going to assume that the characteristic is 0. So assume that the characteristic of the field is 0, right? So we have to show that k is perfect, which means that we have to show that every irreducible polynomial with coefficients in k is separable, right? So let f be a polynomial in k, an irreducible polynomial in k, right? So we have to show that this is a separable thing. But now we make the following, we recall the following thing. We recall that a polynomial is inseparable if and only if its derivative is the zero polynomial, right? So in our case, we have to show that f is separable, so we have to show that its derivative is not 0, right? But since f is irreducible, worst case scenario, its derivative is going to be something constant, but not 0, right? Therefore, this relation over here implies that f is separable, and this proves that the field k is perfect. So now all we have to do is prove two more things, right? So we have to prove, let's see what we have to prove. So one thing is that if the field k has characteristic p and k to the p is equal to k, then we have to show that k is perfect, right? This is one implication. And the other implication is to assume that k is perfect and show that either it has characteristic 0 or this thing happens over here. So if k is perfect and its characteristic is 0, we're done. So we have to assume that characteristic is p and show this equality over here. So in reality, we have to show the following thing. Okay, let me just write it. So we have to show the following. So we have to show that k is perfect. So every irreducible polynomial in kt is separable if and only if when the characteristic is p, right? So when the characteristic is p, we have to show that k is perfect if and only if k to the p is equal to k, right? But instead we will show negations. So we prove that an irreducible inseparable so we show that the negation of this proposition here, so an irreducible polynomial, an irreducible inseparable polynomial in kt exists if and only if k to the p is not equal to k, right? So this is the thing we want to show, right? So let's start by assuming that the right thing is the thing on the right is true, and let's show that the thing on the left is true. Okay, okay, so if k to the p is not equal to k, then since k to the p is always a subset of k, this implies that we can find an alpha living in k, and alpha is not an element of k to the p, right? Okay, so we consider this polynomial t to the power of p minus alpha, right? And this is a polynomial with coefficients in k. Okay, so the first claim is that t to the power of p minus alpha has only one root in some splitting field. So as you can probably hear, it's raining outside, but it doesn't matter. So okay, so the first claim is that t to the power of p minus alpha has only one root in some splitting field. Okay. So of course we know that it has at least one root in some splitting field, right? So the idea is to show that it has exactly one, and this is going to have some multiplicity m, some multiplicity p, exactly multiplicity p, and therefore this particular polynomial is inseparable, right? And then we're going to prove that it is also irreducible over k, and then we're done. Okay, so it's true that we can find some b, not necessarily living in k, such that b to the power of p is equal to alpha, right? So this thing has at least one root. Then, if we take the same polynomial, we can of course write this thing over here, because we assumed, I can take the p out because we assumed that the characteristic of k is equal to p, right? Okay, but now of course we clearly see that b has multiplicity p, right? So it doesn't. So we found one root, at least one. It has only one root, and this root is repeated. Then therefore this polynomial is inseparable. Okay. So in order to be done with the first implication, we only have to show that the same polynomial is also irreducible over k, right? So let me make the following claim. Right. So when I say irreducible over k, I mean it's an irreducible polynomial with coefficients in k, right? Okay. So how do we do this? Okay, since this guy is just t minus p to the power of p, all the possible non-trivial and proper monic factors of t to the p minus alpha are the polynomials t minus p to the power of m, where m lives inside this guy over here, right? So m can't be 0, and it can be p, because I assumed I want to consider non-trivial and proper factors, okay? So of course these polynomials, I mean in general, they're not going to have coefficients in k, right? But let's assume that since these are all the non-trivial proper monic factors, let's assume that t to the p minus alpha has a non-trivial proper factor in k, right? Therefore, so if t to the power minus alpha has some non-trivial proper factor in k of t, then it's going to be one of these guys, and therefore we can find an m living in here, such that a t minus b to the power of m is going to be inside this polynomial ring, right? And therefore if I just so if we consider the coefficient of t to the power of m minus 1 then this is going to be an element living in K, right? So the coefficient of t to the power of m minus 1, which is it's easy to see that this is minus m mod p times b. So this guy is going to live inside K, right? And let me remind you of the fact that since K is of characteristic P, it contains the integers modulo P as its prime subfield, right? So this is why I have this M mod P over here, not just M. Now, of course, since M runs from 1 to P minus 1, this implies that this guy over here, this is not going to be this is going to be an inverse, right, inside FP, a multiplicative inverse, of course. But this is just, this is of course this is a subset of kx, right? And this implies that I can multiply with this with the inverse, and therefore B is an element of K, right? But if B is an element of K, then B to the power of P is going to be an element of K, right? But recall how B to the power of P is actually alpha. B to the power of P is going to be an element of K to the power of P, right? But B to the power of P is alpha. Therefore, we just showed that alpha is an element, is a P power in K, but this is wrong. This is a contradiction, right? Because we assume that alpha doesn't live in here. Therefore, this is a polynomial. This is inseparable and irreducible, right? And it has coefficients in K. So this is one. We just showed one implication, right? We assumed that maybe I should recall it. So we assumed that K to the power of P is not equal to K, and we showed that, and we constructed an irreducible inseparable polynomial in K, right, over K. So the next thing to do is assume that I have an irreducible and inseparable polynomial in K, and then show that K to the P is not equal to K, right? Okay. Okay, let me just start completely. Okay. Oops. Okay. Okay, so let f be a polynomial in here, and I assume that this is irreducible and inseparable. Yeah, okay. Now, what we do is that we use again this relationship star that we had, which said that a polynomial is inseparable if and only if its derivative is equal to 0, right? So therefore, since we assume that this is inseparable, the derivative is going to be 0, right? But now let's think a bit. F is a polynomial in T, and I take its derivative, and this is the 0 polynomial, which means that all of the coefficients, the new coefficients of f of the derivative, have to be 0. But I'm working over characteristic P, and therefore this means that they all have to be 0 modulo P, right? They have to be 0 mod P, which means that they have to be multiples of P. So when I took the derivative, my polynomial f has to be a polynomial in the variable t to the power of p, right? So f has to be a guy living in here, not just kt, but k t to the power of p, right? So let's write. So let's take a polynomial f and write it as so alpha m t to the power of pm plus alpha m minus 1 t to the power of right, and this is this is a guy living in here. So we want to prove that k to the p is equal to k. So let's assume in order to get a contradiction, assume that k to the power of p is actually equal to k, right? Then, since all the coefficients here, all the alphas here live in k, it's true that for every I live from 0 to m, I can find a bi living in k such that alpha I is just bi to the power of p, right? Hence, if we just take, if we just continue writing from f over here, okay, so this is going to be b to the m to the power of p. Let me just write this. Right, b1 to the power of p tp plus p0p. But now again, we use the fact that we're working over a characteristic p, and therefore we can just pull all the p's out here, right? So this is just pm tp plus tm bm minus 1 tm minus 1 b1 t plus b0, and all this is going to be raised in p, right? But now this is a contradiction because we assume that f is irreducible, right? But clearly, if this is true, we can just break it up into smaller pieces, and yeah, this is a contradiction. Hence, k to the power of p cannot be equal to k, and this finishes the proof of our main theorem. So let me now give some examples, some basic examples. Okay, so some basic examples of well, pretty much the most basic examples of perfect fields is, well, first of all, as we mentioned, when k has characteristic 0, this implies that k is perfect, right? So everything over q really means that is separable, right? Every irreducible polynomial with coefficients over something that has characteristic 0, so with coefficients in extensions of q in general, is going to be separable. So characteristic 0 is nice, but one other important class of fields that are perfect are the finite fields, right? Finite fields are perfect. So of course, finite fields have necessarily characteristic p. So in order to show that these are perfect, we have to show that so if f is a finite field, we have to show that f to the power of p is equal to f, right? And the way to do this is to consider the map going from f to f, just taking an x and mapping it to x to the power of p, right? Now, since f is a field, this clearly implies that that this is injective, right? So phi is injective, but since f is finite, it also implies that phi is surjective. Therefore, if you give me any element here, I can always find another element in f such that its image under phi, so a p power is going to be equal to the first element, right? So it follows that k to that f is a subset of f of fp, right? Which, of course, this gives us equality, and according to the theorem, this implies that f is perfect, right? So characteristic 0 and finite fields are always perfect fields, and these are probably the most important class of perfect fields. Now, let me just mention another theorem, which I don't know if I'm going to prove it, even though it's not really that hard. So another characterization says that k is perfect if and only if every finite extension of k is separable, right? So an extension is called separable if and only if the minimal polynomial of every element is a separable polynomial, right? Yeah, so it's not really that hard to prove. I mean, maybe I can just sketch it, even though it's not that hard. So if k is perfect, and we want to show that every extension is every finite extension is separable. So if L is such an extension, just consider an element living in L, and then just take its minimum polynomial over k. Now this is going to be an irreducible polynomial with coefficients in k, but since k is perfect, every irreducible polynomial with coefficients in k is separable, right? Therefore, this guy is separable, and by definition, this implies that the extension is separable. And if we want to go to the other direction, let's assume that every finite extension is separable, and we want to show that k is perfect. So let f be an irreducible polynomial with coefficients in k. So we know that we can find some alpha such that f of alpha is going to be 0. Alpha is going to live in some splitting field, right? And then we consider, the trick is to consider k alpha over k, right? Actually, maybe my notation is not so good. We want to consider this extension over here, right? And of course, and we know from field theory that the degree of this extension is going to be the degree of the polynomial f, right? Therefore, this is a finite extension, and by assumption, this has to be a separable extension, right? Which implies that the minimal polynomial of every element, in particular of alpha, has to be separable, right? So f is separable, and we're done. So yeah, these were two characterizations of the so-called perfect fields, which arise pretty frequently in at least in algebraic number theory, for example. So thank you for watching, and see you in the next video.